Hello, welcome to the stream. It's been a couple weeks since we had an Essentials of Compilation stream, and because I was on vacation, had a great vacation, got a lot of sun, which you might be able to see on my face, and we're gonna get started. So where we left off, I believe we were doing the explicate control pass. If this is your first time to the stream, welcome. And we are building a compiler from a variant of Racket into x86 assembly, and we're doing it all in Gleam. We are in chapter 7 of this book called Essentials of Compilation, and it is a method for building a compiler which starts with very simple transformations and gradually lowering the original source language into x86 assembly with very small transformations. Some of them are complicated, but none of them are huge. The biggest ones are the ones that convert from a Lisp shaped language into the imperative C-like intermediate representation or language, and then there's some of them that remove specific language constructs. So, for example, there's a transformation which changes complicated nested expressions into ones where you can only use variables or constants, for example, as arguments to particular primitive operations. And then there's also ones later which are much more about data flow and understanding what resources are available so that we can allocate registers. And those are the complicated ones, but for the most part, they are very straightforward. I'm going to take an entire program that we have specified, and I'm going to make one transformation on it, but handle the entire potential syntax tree. So there's a lot of this, is shaped like a lot of case expressions over forms that exist in the language syntax. So, and then as we work our way down, we remove some things that are considered normal in a higher level language, but we reduce their semantics. So, like, we'll expand things, we'll make simpler operations out of more complicated ones. And then finally we get to turning this, the big one here, which we did last time, the explicate control. We turn a very expression-oriented language into an imperative one where you are performing one operation and assigning it to a variable and perform another operation, and it's like a sequence of instructions, right? So let us have a look at where we are. And I will stop the bloviating and we'll flip over to code, because that's what this stream is about. So we have this high-level language, fun for function, because we can have user-defined functions. And so just as an example, if you're new to the stream, welcome. We have types. This is a typed Lisp. And the types are integers, booleans, voids, vectors, which are kind of like structs, or you could think of them like variants in a Gleam type, and functions, which are has arguments and return type. And then we have a bunch of primitive operations. We have expressions, which can be made up of other expressions or primitive operations. We have some internal things for our compiler, like type annotations. So when we first parse, we don't get any of these has type things, but then when we do the type check pass, we will wrap certain things with has type. It helps with variable allocation. I'm sorry, not variable, vector allocation. So if there's a vector that appears somewhere, we use this has type to say, hey, it's this, and that lets us inject allocation, garbage collection type things. We have function definitions, and then we have our two forms of our program. And we could have done this differently. I could have made a completely different intermediate representation, but this is basically like the body expression becomes a definition of the main function. So, all right. Let us. So we did explicate control last time, and I think that the main thing I wanted to make sure is, so we have some to-dos here. Let's make some tests that we can check that our explicate control does the right thing. And so explicate control is all about understanding of any particular expression or any particular subconstruct of the language, what position is it in, and it has a bunch of different ones. So the tail position is like if this is the main function, or inside a definition, an expression in tail position means that this thing will be returned. Assign is like a let binding. So if you put an expression inside the binding of a let, then it gets treated as assign position. There's predicate, which is in the condition of an if or a while expression. And then there's finally effect position, which is only relevant to begin expressions. So begin expressions have a sequence of sub-expressions where only the last one is returned from it. So use that for the body of loops. And that's effect position. So, so let's look at this. So a call and expression position. So this would be what do we call these tests? So this is explicate control, tail call function. Let's see, call expression test. Let's just call it that. Let's make one for effect. And the main thing that we're trying to do here is make sure that we have good coverage for this transformation with all of the new constructs. So all right, so in expression position, so I think that this is, so we look at an example here. This is tail call. And we define a function called inc for increment that adds 1 to its argument and returns that. And then the body of our program is increment 41. So the return value of our program always has to be an integer. In this case, it's going to be 42 because that's what we do. So that's for tail call. So I think the expression would be like, it's going to be in a sub-expression, right? So let's do program let's do define, and let's just copy this inc function. And I want to, let's see, explicate. Expression position doesn't make any sense. So I think probably what was meant there was, yeah, assign. I think I meant assign position. Okay, so we're going to define inc again, and we're going to do let A is inc of 40, and then we're going to do plus A1. Okay, so that's going to be in assigned position. And okay, so that's going to panic, but at least we can get the type there. So we could do something like this. We know what the definition is going to look like, right? Because we just copied it. So let's construct it. Okay, so we're going to need something like this. Yep, that's the correct definition. Okay, so this is going to be all that integer t, and then c dot blocks. Oh no, that's not right. We have c dot blocks. This just needs to be a tail. So yeah, it'll be, let's just close this so that we can have correct syntax. And I have something wrong here. Okay, so I have a definition inside the definition. That is not correct. What I need to do, put another paren there. All right, what do we have going wrong here? Excuse me. We're going to figure out what this is. Okay. All right, let's make something up. Let's just say a read statement and then fix it. So, all right, so blocks. It's missing prefix. Yeah. Okay, so that's wrong. That's fine. We can fix that. So looking at this program, what do we expect here? We expect um, a sequence, and that's going to take a statement and a tail. So a statement is sign, and this is going to be a.1, I'm assuming. It might be a.2. I'm forgetting how that uniqueness algorithm works. Okay, so it's going to take a.1 and an expression. It's going to do call. So call is takes an atomic. So it's going to take a fun ref, and that's going to be ink and 1. And then it's going to take a list of atomics. Wouldn't you like to use Birdie for the tests? Yeah, I like to test my own knowledge, though. Birdie is great. Hi, welcome to the stream. I've used Birdie on a thing at work, and I really enjoyed it. I think it was best for that, though, because what I was testing was like a lot of rendering of luster components, and it was great for that. So it was a small project. I was solo on it. I snuck it in because it's what I wanted to use, and the technology didn't matter. So, you know. Okay, so we're assigning a.1. Okay, so, and then the argument here needs to be int. So these have to be atomic, right? So funref is atomic. No, funref is expression. Okay, so what we're probably going to see, so variable, so we'll have temp.1 here, right? And then this will be wrapped with another assign, because okay, and I'm going to need to start indenting this because I'm getting lost. Because function references, the way we do calls is by indirect references. So it'll be like put the address of this function into a register, and then when we do the call, we dereference that register. So we treat that register as a pointer. So there's going to be an assign here, which is followed by this. And I'm guessing this is going to be a.2. The thing is, the remove complex operands pass is different than the uniquify pass. Okay, so that's the call, that's the assign, and then finally we have we need a tail. Our tail takes an expression, so we can do prim and I think that what we'll do is on this we'll wrap this up and then we'll see, because I think that the main thing here is that the variable names are going to be different. There might be some order of operation differences. That's okay. Okay, so that sequence is closed. that sequence is closed, and now we're syntactically correct. Okay. So let's we're just gonna echo nothing, echo nothing. I don't want these to fail for no reason. Okay, so this is rather than to do, it's gonna be P2. So let's run that test. And yeah, so we got a little bit different from what they have. Okay, so looking at this briefly, yeah, we've got the right-hand side is what we wrote. The left-hand side is what they wrote. Okay, so main, yep. Block main is sequence assign temp.1 funref inc1. Okay, assign a.1 call variable temp1 int40 return prim plus variable a.1 int1 main. Okay, so the difference is the naming of this variable. So that's the only thing different. Hey, not bad for guessing how it was going to work. Let's run the test. And yep, okay. So we can get rid of these echoes, and then we can just actually do that. Okay, so effect test is, we do a begin. So let's make a program that has a call, and we'll use our trusty inc function because it's easy. Maybe we should call it unc because that's what I was called a while back. Okay, so in this one, I want to do a begin, and I want to say inc1 and return 42. Okay, so this is going to do nothing, right? But I think what we can expect, and I'm just going to copy this business and modify. Actually, let's copy all this. Okay, so we know that this is going to fail because it's got a different thing. So we're going to have a sequence, a function call in effect position should be we assign this, so we still have the temp1 assign, and then let's look at this definition. We don't have a call statement. So I think that what this will need to do is assign to a variable that gets thrown away. And I think that's what we did. So let's just assume it's temp.2. And then return is going to be, what did we say? 42. Of course we did. Easy to remember that way. Okay, so I think that this is what it's going to be, but this will probably be x.1. Let's find out. Okay. So, yeah, there's a to-do on that. That's fine. Okay, so we've got main, we got assign temp1. Okay, so it's actually using the prefix and it's saying main apply _1. So let's just rename the variable, and I think that will be fine on that. Okay, so the interesting thing there is the structure of that makes sense with respect to what we expect out of this pass. So that was nice. Okay, and then basically a funref in effect position. I think this will just be thrown away. Hi, Willie. Welcome back. Got my 2 super fans here today. Loving it. Okay, so a fun ref in effect position. It's basically like this. Because this is a valid expression, right? It just doesn't do anything. So I think that what will happen is we just remove it. Remember, we're not doing any optimizations here, so let's see if this is correct. It is. So that is doing what I expected. Well, no, I'm sorry. That test never passed because it didn't do any assertions. Boo. Okay. Okay, so we got slightly different. Let's see what's different. Okay, so the left is what was actually created. And it's completely removed. Interesting. So it's never assigned. Our main just becomes return. That's good. That means we're not generating dead code. And I think that that's pretty good. So let's quickly make a commit for that. And we're gonna say complete, more complete coverage of explicate control. Okay, and I'll push that. So our next bit, which is the whole point of the stream. Thank you for sitting through about half an hour of that, finishing tests. Is we're going to talk about select instructions. So let's just close all, and then we'll start over. So last time, what did we do? We did, when I say last time, I mean last chapter. The last chapter, the x86 variant we had was global. This is the global variable things, because we needed those. They're set up by the runtime of our language to have pointers to the heap, and the garbage collector and all that. Those variables, those global variables, are used by that. So this is the one that we need to base it on. Okay, so here they'll have, like they've done before, 7.9. So we can see what's new, right? Okay. So let's duplicate this, and we will call it, what do they call it? x86 def call q star. Why do I have to make it so hard? We'll just call it def call q. Okay, so the new instructions that it has are call q star, and it takes an arc. It has tail jump, and yeah, so we'll say tail jump, and that takes an arg. And it has LEAQ, load effective address. Interesting, that takes a register. So LEAQ takes an argument and a register. Right, because what we're doing is we're saying you can't go memory to memory. This could be a register, this could be a memory location. You have to go into a register and if you need to go from one memory location to another memory location, you go through a register. So there we go. Okay, so that's that. Blocks are lists of instructions. Why is that plus? Okay, so that's saying that it needs to be non-empty list. There's this def thing. We're going to have to see what that is. Oh, it's a definition. And it's .global.align 8 label. What am I supposed to do with this? Oh, okay. So this is just saying this is the structure of a definition. So we need to do a definition. And these are like concrete syntax, right? We can just assume that that's this. And what we do is we say definition, labels a string, and blocks is basically this. Okay, so they have the abstract syntax down here. Okay, so they're calling it indirect call queue. Tail jump. Okay, so definition is going to have a lot of the same things as we had before. I don't know what else is going to go in here. Notice all this stuff that we used before. Probably going to have to be restructured by future phases, but okay, so tail jump. Why don't we call it indirect call queue just to be consistent with what they have there, even though I don't care for that. LEAQ. Okay, so block, same stuff. The info has the live before and live after sets. That's no change. So definition, label, type. And we need to change this from L-tube to L-fun. What did we... I think that's just the return type. It could be that we give it a fun type, but we're not going to be rewriting any of that logic. So I think that probably is I'm curious what this type is used for at this level. Maybe it's used for the interpreter, because one thing that we haven't done through this series is actually written the interpreter for the x86 level. We have it for the high level, the highest level, but we don't have it for the x86. Which that wouldn't be that hard to write, because we're using so few instructions, but I just never have bothered. Okay, so let's see. Let's see what they say. We're gonna have to read because I think I just tried to jump ahead. Okay, so the idea of select instructions is we turn that C-like language into an x86-like language, x86 assembly-like language that happens to have variables We eventually get rid of the variables, but that's done with the register allocation pass. So, okay, the definition of its concrete syntax. Yeah, okay. So use the align directive on labels of function definitions to make sure the bottom 3 bits are 0, which we put to use in chapter 9. Okay, so chapter 9, dynamic typing. Okay, so let's, and I just lost my place. Fun. Okay, 7. So they're using dynamic typing. So they're putting a type tag on values, and that's why this exists. Why the align directive exists. Okay. An assignment of a function reference to a variable becomes a load effective address. Right. So if we have this equals funref something, then it's LEAQ with the indirect addressing using the RIP register, so the instruction pointer register. RIP, me. Okay, so that's pretty straightforward transformation. Okay, regarding function definitions, we need to remove the parameters. Right, so the parameters don't matter because they will be put into registers. And we already handled that. We already dealt with it by making sure that they're never more than 6, which is this, the Unix CABI calling convention is 6 registers on x86-64. So, okay. So really, this is the return type. I think that answers what I was concerned about. Okay, regarding function, when you remove the parameters, instead perform parameter passing using conventions. Yeah, so the arguments are passed in registers. We're going to turn the parameters into local variables and generating instructions at the beginning of the function to move from the argument passing registers to these local variables. Right, so when we encounter a definition from whatever intermediate, Elmon funref, I think it was. No, cfun. When we have a definition in cfun, then what we do is we take those arguments and we change them into assigning them to variables. So grab the register, put it in that variable. Turn the parameter, okay, generate instructions at the beginning of the function to move from the argument passing registers to these local variables. The basic blocks B prime are the same, except that the start block is modified to add the instructions. Right, so they had called it start. Earlier in the chapter, they didn't give us guidance about what to call the name of the block that that entered the function, and I was just like, hey, call it, the name of the function, which seemed reasonable at the time. So, for example, if we go look at the tests that we just wrote, like, the entrance point for main is a block called main. The entrance point for inc is a block called inc. So what we'll need to do in that translation is grab this grab the definition of the block for whatever the name of the definition is, and then put those register copying in it at the front of it. Hello, welcome Jake Pie 3436. Welcome to the stream. Drop any questions you have in the chat. Okay. So we don't have a start block for these. And I think it was that I was a little bit paranoid about having collisions. And it looks like what they're suggesting here is that you rename it with the function name fstart. And I don't actually care. We're just going to use the function name. It's fine. The difference might be let's read it a little bit further, because I think the difference might be that sort of like in our original where we do generate prelude and conclusion, we have to do that same sort of step for every function definition, in that it needs to handle caller and callee saved registers, stack, etc. So we probably need to, when we go shift this, we rename it to, like inc start or main start. Okay. And then there's the conclusion of the program, right? Follow to jump to conclusion. There's a start block and conclusion for each function, but their labels need to be unique. So they prepend the function name to start and conclusion. That's fine. We can do that. I think you can't use type as a label. What do you mean you can't use type as a label? Oh, on the yeah. Like, this can't be a field label. We only care, what I was trying to get to in the text was, is this the return type or is this the type of the function itself? And it's just the return type. They're saying, you get rid of the arguments, because the arguments are already set up to be passed in registers. Okay. The interpreter needs to be given the number of parameters for the function of the parameter. We don't care about the interpreter. Numparans. Okay. By changing the parameters to local variables, we're giving the register allocator control over which registers or stack locations to use for them. Right. So if you implement the move biasing challenge, which we didn't, the register allocator will try to assign the parameter variables to a corresponding argument register, in which case the patch instruction pass will remove the move queue instruction. Right. This happens in the example, and we didn't do the move biasing challenge, so I wonder if this will still happen. This feels like magic. This is not magic. We're just transforming data in very specific ways, but I think the hard part is holding in your head the entire process. Which is, it seems like every time I come to, revisiting the same pass with new features, it's like, oh, that's what this pass does. So yeah, I completely understand Renaud. It's a thing. Okay, so which case patch? Okay, this happens in the example translation of figure 712 in the add function. Also note that the register allocator will perform liveness analysis on the sequence of move instructions and build the interference graph. So, for example, x1 will be marked as interfering with RSI, and that'll prevent the mapping of x1 to RSI, which is good because otherwise the first move queue would overwrite the argument in RSI that is needed for x2. Okay, so I guess we need to look at that example to understand, but I think that what they're saying here is that putting the move instructions to copy the arguments into the variables helps the register allocator. Okay, which totally makes sense. Like, even if they become eliminated later because they're a redundant move from a register to the same register, then that's fine. In the mirror image of handling parameters and function definitions, the arguments are moved to the argument passing registers. So this is about the call side. Note that the function is not given as a label, but its address is produced by the argument arg0. Okay, so let's see what they're saying. So they're saying if you have this, which is assign the value of LHS or assign to the LHS variable the result of calling this function with these arguments. And then it's like iterate over the arguments, putting them in the callee save registers. You're putting them in the argument registers. And then you do call queue, the indirect call queue on this argument, right? And then when you're done, you move the REX register, which is where the return value is always placed, into LHS. So this is the form that will generate when we get a call. Can you remind the audience at which point are we in the compiler development after you're done reading that, of course? Okay, yeah. So this is a good good time to look at this, not thumbnails, table of contents. So over a year ago, we did very basic integers and variables. So that was compiling very primitive instructions and variable assignments. And then we did register allocation, which is one of the more complicated things in that it needed its own chapter, even though it's basically 2-3 passes. After that, we did Booleans and conditionals. So you can have branching, you can have Boolean types. So we started with just integers, and then we figured out how to assign those variables to registers. And then we did branching. So you can do if. Then we did loops, which is an extension of conditionals because you need a termination condition, right? It also introduced immutable variables. So before this, there were only lexically scoped immutable variables. For loops, you need to change something that is part of the condition. So while, the while expression, you can mutate a variable that will be part of the expression that determines whether you terminate the loop. And then the last chapter we did, chapter 6, was tuples and garbage collection. So those are like, in our Lisp language, this is a tuple. We just didn't name them. They're just, integer indexed fields. And they have no tag on them. So it'd be like vector, string, type, whatever. And so that was that. And now we have user-defined functions. So before, we only had runtime defined functions and primitive operations. The error you have? Which one? Which error? Oh, this? Oh yeah, it's mad because I haven't filled in the rest of the instructions. And this is really just about formatting them. That's fine. But we also need to change the structure of our, so I got a little sidetracked. Let's go back up here. We know that now an x86 program is, all these other things, but it's no longer a body. It's a list of definitions. So we're going to change this to defs, and this is going to be, should we use a dictionary? Did we do that in the C fun language? No, we just did list of definitions. It's fine. List of definition. Okay, now it's like, hey, did you mean body? Oh wait, this is wrong. Wrong place. This is, let me see, list of definition. The interesting thing here is these types. Where are we using these? It's just these two places. Well, I mean, I guess we need to find all the places where this is referenced. But it's not going to be referenced anywhere because we haven't imported that to anything. So let's look at this one. And let's see where we reference. I don't know if this even works. Nah. Can we find all references to that? Okay. So new program. I don't recall what the types are even for at that point. I'm sure that we populated them somewhere. Oh, okay. So this has to do with tuples, the garbage collector, callee save registers. Oh, right, because the GC could use some registers. Okay, I think that there's going to be some interesting changes we have to do here. We're not at this part yet, but I think that we might need to put this information about conflicts. So conflicts is a graph from locations to interference graph nodes. So if you're not following, interference graph, a node is an x86 location, so it's either a variable or a register, and whether it has been assigned a register, and then what registers it is in conflict with. So which ones it cannot be assigned. That's what the saturation is. So okay, so it's saying this is all variables. Okay, if the variable is a... All right, so I guess we're building this. I just want to make sure I'm not going to mess something up. I don't think it is. I think I'll just leave it. Okay, so we'll just leave that. And this is going to be an empty list. And we're going to rename that defs. Okay. All right. So now we have a new challenge. Let's get our pretty printing going for this, and then we'll get to actually generating the instructions. So I think that this is going to be interesting. All of our stuff needs that global align 8 that they talked about up here. Not explicate control, it's this stuff. So even main gets this global align 8. And I think that what we do is we kind of repurpose this format block. And by the way, global only says this is something that the linker can see. Other blocks it cannot. Okay, so I think that what we're going to do is we will take input.defs and we will do list map, and we're going to say format definition, and then we will... Sorry, my cat's on my lap and making it really hard. Okay, so we're going to pipe that to the concat join. So we need to do this. Let's generate that function because I'm lazy. Let's go to make it pub just in case. So here's where we're going to do the... this thing. And I think that what we do is we'll say, we'll make this take an argument, which is definition string. And if, yeah, so we'll say definition. And if this is true, then we're going to say dot global dot align 8 definition. Okay, so that will make sure that we get that prefix on there that says, you know, this is an entry point into the object file. Okay, so now we can just go. I would really love for the thing to come first, but I think that we just do dict fold. Definition blocks. No, we don't want fold. I will kind of want map values. I want the key as well. We'll just do toList. Seriously? Okay, and then we'll do list map. We're going to say format block definition dot label. Okay, and then we'll do dot concat join, and we do basically this. Yeah, so that's going to make sure that there's new lines between each block. All right, and now we can deal with the missing cases from the format instruction. So let's add missing patterns. So looking at this syntax, tail jump's not actually a thing. It's just jump, but you know, we'll fake it for now. Fake it till we make it. Okay, we're gonna say this is going to be doc concat join with space. Let me see what I did up here. I think I just kind of like did direct concatenation. That's probably going to be more reliable. Okay, so we need this doc from string. This is call queue, right? We need space. We'll just say doc concat. And actually we can combine those. Let's do star. And then this is going to be format arg. Okay. Because this is, you know, we're doing a deref of that, whatever that argument is. Okay, tail jump is just tail jump. And I think that for consistency, I'm going to convert that to function call. Easy enough. And the whole reason we have this pretty printer is so that we can use our web-based interactive tool. And see what it outputs. Okay, and LEAQ, yeah. LEAQ space format arg a and then format register. Yep. I don't know what's going on there. We'll put the comment outside that list. Okay. Yeah. So we've covered all those cases. All right, I think that now we can look at, finally, after an hour, thank you for bearing with me, we can look at the select instructions pass. So first thing we're going to do, this is C fun, this is L fun, and then we're going to have a lot to fix. So the select instruction pass takes, and this is going to be x86 def call queue. Okay, so it's going to take a C program and it's going to return an x86 program. Makes sense? Okay, this whole thing needs to be changed. This is like details about the individual constructs handling, but we need to think about the whole program too, because now it's not just one function. So this is interesting. Select tail is returning the types. So I think that what we need to do here, yeah, and this is a list of instructions. So what we need to do here is basically do this for each function. And then that tells me, this could be wrong, but that tells me that here, this types annotation needs to go on the definition. Because this is about, again, ensuring that those vector typed variables do not interfere with certain registers used in the calling convention. So I think that what we do is similar to how we made this definitions. I think we move this over here. We'll leave it named the same thing. It's interesting, I think the conflicts, these may actually all move onto definition, but we don't know yet. Especially because if you think about, with the exception of tail calls, if you think about how function calls work on x86, it's basically as if our own, like, a whole new program was being called from our perspective of what we did before. In that we have to obey all the same conventions that we enforced at the program level on each function definition. So we have to save all the correct registers, and we have to adjust the stack as needed. So I think that there's going to be a bit of moving this stuff onto the function definition. But we'll see. Okay. So this is going to be, rather than input, we're going to say let defs input.defs and it's going to be basically this dict fold, except it'll be a list fold. No, it'll be a list map. Okay. So we don't know what these arguments, well, this is a def, right? And this is going to be def.body. Excuse me. Wow, I was really not happy about that. It is not. Oh, for Pete's sake. C fun. It's a list of definitions. What? Okay. It is not happy. The imported module has errors. What are our errors here? Oh, we got rid of types. Okay, now let's see if it'll. Okay. So here, what we're going to do is we're going to return x86.definition, and that's going to be fill the labels, please. Okay, so the label is going to be def.name. The return is going to be def.return, and then blocks. Let's rename this to blocks. And types. Okay, so this is def.blocks, right? No, it is def.body. What's wrong there? Oh, okay. Yeah, we want that. All right. So I think that this is we're basically doing the same thing there, but now we need to handle the new stuff. So look at those errors. Aren't those fun? Okay. So this is basically we need the new things. Okay. Add missing patterns. Okay, so this is select a select statement. Okay. What did I do wrong? No. Select statement. Okay. So assigning a variable to a function ref. So this is going to be, we always return a list of instructions and any types. Okay, so we know. Uh, well, we can't really. Are we even assigning the type in any of the ones that aren't vector related? I don't think we are. No, we are. Okay, the problem is we can't assign that type without looking up. I suppose we could do that. But then we're going to have to pass some more stuff in. So I think that what we'll do is I'll put a note here. And it looks like actually for this one we're going to need it because we need the call. We need to know what the return value of that function is, the return type. So we need to be able to look it up. Okay. Maybe we need to fix this now. So let us let's call it fun types because they're very fun. Okay, so we're gonna input defs list map, and then we'll do dict to list, dict from list. Okay, so this is going to return d dot name, and then it's going to do L function type d dot okay, so that just takes a list of types, right? So function type takes and here we're going to have to go arguments map pair dot second, and then finally d dot return. Okay, expected 2 arguments got 1. I got those parens mixed up. Okay. Let's just do a regular function call there. If that doesn't make sense, bear with me. So what we need here is to pass through like all the function types. So whenever we encounter a fun ref or a call, then we know what the types of those functions are. And we can go look at this and go, hey, what's the return type of that? And I can assign that type to that variable. So we're going to treat that as immutable. And let's go down here to select tail. And honestly, this is fun types. Is going to be a dictionary of string to L.type. And let's just add that to everything. We don't need to modify that. Okay. Let's go back in here and we'll have to fix some other things, but let's get down to our bits where we didn't generate anything. So here, what we need to do is I'm going to say let assert OK. T is dict get fun types for name. And then we'll do types, insert the variable name and then t. Okay, so that will augment that local variable thing with the type of the function. So we don't care about the arity. Honestly, it might be better to do index the fun types by the whole funref idea, and that would be possible up here. The problem is funref is not a type of its own. It's an expression. I could do, the key could be tuples of name and arity. But we're not allowing we're not allowing name collisions. So we're not allowing functions with multiple arities. Okay. So now the thing here is, yeah, so that's a fun type. That's a function type. Language server rocks. Oh, I totally, yeah. Like, it helps me all the time. Okay. So let's do another let assert here. What happened? Okay, there we go. So function. Now we can say, and we'll figure out what this is. This is the essence of things. We want to insert into types var t.return. But here we're going to do, this is going to be l.funt. Except we're going to do return. Okay, and that's the return type. So whatever the return type of this function is, and we'll eventually use arguments here, but oh, there's a problem here. We need to know the type of the local variable. This is atomic. So luckily with this, I think that what we do is we need to also pass the locals, and maybe what happens is rather than just being the fun types, this is the types of locals. So in select tail, because we call select tail recursively on itself in sequences, right? So we need to track the types of local variables, which the problem is that becomes order dependent because we don't have any. We haven't done data flow yet. Oh, this is rough. We're not doing this in data flow order. We're doing this in arbitrary order. Okay, for now, we're gonna have to fix this later. I don't know any other way. But I'm sorry, I'm gonna have to back up a big way. And we're gonna get rid of those arguments, the fun types arguments. Okay. So we are going to have to play fast and loose right now. I think that the problem is I didn't build up the correct structures for this. So when you do a call, when you do a fun ref, we're not going to update the types. The arity gives us enough to know, well, the number of arguments gives us enough to know which registers to put things into. So let's figure that out. Let's figure these two things out. Okay, so fun ref is basically this. So we're going to make LEAQ takes an argument. So actually, there's something wrong there. LEAQ takes an argument and a register. But we don't know the register. Sorry, I'm getting a little bit lost here. So what we did previously for that, yeah, we didn't put it in here at all. Let's look at this. When we did the call queue label arity, yeah, just call queue label, ignore the arity. Oh, right. So this is global. So the arg has to be global. Label RIP. Okay. So This is global name. And then the problem is this needs to be a register. I don't understand how they expect that to be a register where here it's like okay. LHS is the translation of LHS prime is the translation of LHS from atomic in CFUN to arg in our call queue whatever. Funref becomes a global AST node, right? Whose concrete syntax is instruction pointer relative addressing. Right, so we have that before. We just do select ATM. See variable var. Is that what we do? The thing is that's going to be right, it's going to return an arg, not a register. This is where like these little consistencies jump out where I'm like, well, if your programming language that you wrote this book in required it, you might actually need to do something different. Okay. So yeah, what I'm trying to look at here is what do we do on some of the other assigns? Let's do a simple one. Okay, we just, yeah, I think that what we need to do is we need to relax this LEAQ from register to arg, which means the thing that we just wrote will be correct. Okay, so that's fine. But I think that what we need to do here is similar to what we did here. That returns an arg. And then, oh boy, is the language server's messed up. Okay, so let's jump to select ATM again. So that returns an option of a type. Yeah, it's going to be none. That's not an atomic. What's this V? Honestly, I think we just do var of var. I think that's just what we do. That's essentially this. Okay, well, we're going to need to deal with tail. But also, I think that we're going to have to, up here in our, I think we're going to have to extract definition here. Like select definition as a thing, rather than select tail. That would be a good idea. But let's handle the assign of call. So this is going to be, let's see, we're down here, call. Okay, so here we need to do ultimately we're going to have x86.indirect call queue, and the function is going to be atomic, so we need to do a select, sorry, what is going on here? Oh, I'm a bonehead. Okay, so we have indirect call queue, and this is going to be, we need to append. So what we're going to do is we're going to we're going to map over arguments, and I think this is going to need to be index map. So if we look at x86 global, or maybe we zip, where is it? It's like the callee save registers. Wow, okay. Not x86 global, I'm sorry, the base. Here we go. We probably need one that says argument registers. So let's do that. Argument registers is a list of register. Okay, so then we can go wow, it is really not happy. I think that we need to go up here. And I need to find what the calling convention says on the registers. Okay, here they are. So we'll just copy and recapitalize those. So this is RDI, comma, RSI, comma, RDX, comma, RCX. I have no idea why this calling convention is the way it is. It's so weird. Yeah. Okay, so these are the argument registers. What we'll do is let's do arguments zip with base dot argument registers. And then we will do list map. So this is basically telling us which register to put it in. Oh, for Pete's sake. You can tell it's getting toward the end of the stream. I'm losing it. So what we want to move is it's always origin destination, right? No. Yep, origin destination. So we move Q from A to okay. Let's talk this through because I think I'm getting dizzy a little bit. So we're going to ignore that for now. We're not putting it in there. We're not caring about types of function refs or calls, although we should. Okay, so basically we're taking all the arguments and we're moving them into the call registers. And then we do indirect call queue. And then the last thing we do is we do a move from RAX into the var, right? Because we need to capture the return value of that function into the variable that it was assigned to. Is list zip even a function? It must be, otherwise I'd be getting errors here. So I think I need to look at the semantics of that real quick. So if one is shorter than the other. Okay, yeah, that makes sense. It's behavior that we want. And I imagine this is implemented as a self-recursive. Yep. And then finally reverse, yeah. So if there's at least one element of each, you add them to pairs, and then you at the end reverse. Okay. All right, so gosh, we did one function. Let's look at select tail because I think that's important. the other thing that we need to do here is we need to... What is going on? What's wrong here? Error. Oh, this is B. And we'll say format arc. B. For Pete's sake. Okay. I think that let's extract this function. And that's basically this. And then this will be select definition. And we can convert to function call, remove block. Okay. Then we can focus on doing things here. So now this, actually we need to pass into select tail the def name or def label, because we're going to need to know we're going to need to jump to main conclusion and main start. It's just main conclusion. Okay, so the definition or the label is a string, and this is label conclusion. So wherever we're doing a return, maybe let's just say let conclusion is that. And then any place we have this, we can just say jump to conclusion. I should just do find and replace because there's a lot of returns here. Okay, so now we need to add the missing patterns. So interesting, returning a fun ref is valid. So interestingly, return of call should be a panic, because that should be a tail call. We will say normal call in tail position. That's a bug in our compiler. And I want to move, like, keep these panics at the bottom. Tail call is fine. Returning a fun ref is fine. And we can ignore those arguments and function. Interesting. When we talk about functions, it's totally possible for a vector to be passed as an argument and the caller mutated, or the call E mutated, in which case it would return void. I think this is fine to leave in there for now, but we might be able to create, or we might be able to find some pathological programs that exercise this clause. Okay, so let's look back at the book. We need to look at the. Okay, so the start block is modified. This is the first bit that we need to do. So for a definition, okay, so we need to say let let's call it argument moves, we'll call it that. If block name equals definition.name, and we did this previously in one of the other ones. Okay, if that's false, we don't need to do anything, right? If it's true, then we need to do basically like the zip thing that we did for the caller side with the callee side. Label. So we're going to take we're going to take the names, and then we're going to zip them with x86 base argument registers. Okay, and then we are going to, since this is a map, we're going to just, it's not a map, I'm sorry, we have a map operation here. We're going to map that to x86 move q. So we're going to use a register of p.1. So that's moving out of the argument register into var of p.0. Okay, so this gives us, for the entry point of the function, if it's the name of the function name, then we move all of its arguments from the registers into the variables. Okay, and so then body becomes argument moves with whatever the tail is. Right? Okay. It would be easier if it were just start. I just didn't want it to get too crazy. We can probably go back and make that change later. Okay, so now we know The downside is this is constructing this conclusion. So here, let's rename this to conclusion. And then we're going to move this outside. And this is going to be tail so that we only do it once. Not that that's like super necessary, but the other thing that start will have to do potentially is allocate on the stack. So yeah, that'll be interesting. I think it'll be good to see what comes out of this. Okay, so we have some to-dos down here. If we return a fun ref, then let's just return the types unmodified. Let's put this in there as a placeholder. Okay, so return of a fun ref is going to be basically like the assign, like we did in select statement for fun ref. Right, so we do this, except that we put it into REX, right? And this is going to be x86.reg, rex. Yeah, okay, well, we need to have that unqualified. Okay. And then it's going to be jump to conclusion. Yep. Does that make sense? So because what we're returning is a fun ref, it's just, you know, put that address into rex and then return. Conclusion does the ret queue. Okay, so tail call is especially interesting. You turn it into tail jump. Okay, so for tail calls, the parameter passing is the same as non-tail calls. Generate instructions to move the arguments into the argument passing registers. Okay, after that, we need to pop the frame from the procedure call stack. However, we do not know how big the frame is. That gets determined during register allocation. So instead of generate, okay, so we invent a new instruction and just pop the frame and do an indirect jump, which we name tail jump. Okay, so let's look at the code that we have for the call. Oh. I got that wrong. My bad. Okay. So we can do this, basically, again. So we get the arguments, and then we're going to do x86 tail jump. Okay, and the function is just a name, so that's a global function. No, function can be a variable. It's already atomic. So we need to do Okay, I think that's, let's read this paragraph again. I think that's what we need to do. Okay, for tail calls, the parameter passing is the same as non-tail calls. Generate instructions to move the arguments into the argument passing registers. Got that? After that, we need to pop the frame from the procedure call stack. However, we do not know how big the frame is, right? That gets determined to register allocation. So instead of generating instructions here, we invented an instruction that means pop the frame and then do an indirect jump, which we name tail jump. Abstract syntax for this instruction includes an argument that specifies where to jump, and an integer represents. Okay, so we should. It's interesting that in their table up here, oh, they do have the arity. So I think that what we need to do is adjust our tail jump instruction because call queue has an arity. This is, let's not, can I rename that? No, we'll call it label. That's fine. Arity is an int. And that's going to break some things. So let's jump down here. Label. Arity. Does our call queue format the arity? No, it ignores it. Okay, that's fine. We're just using that for passing around. Remember, this is an intermediate representation. It can have things that don't actually come out in a concrete syntax, so it's fine. So what we need to do here is say label is f, and arity is length of arguments. This is arity. Okay. And again, that has to do with dealing with sorry. Don't care about the interpreter. Okay. So as long as there's no compilation errors in here. Okay, so we are not line 299. Yeah, we're not caring about the arity there. Again, I have concerns about this particular place because of types. In that at this level, when we're processing individual steps, we don't know what the types of those functions are, even though we have them at the top level. And I'm kind of wondering if we should get the function types. The problem is, of course, that, again, we don't know what order. Yeah. I think the bigger problem is when a function returns a vector type, do we have the has type wrapper around it? That's what I'm wondering. Because I think that they get eliminated. We have this. I think that maybe what the answer is, in these places, is to just print them out, because I think that where's the other place? Be in a call and be in tail. Right, so I'm going to move this up, and we're just going to echo FT here. And then for, yeah, we don't have that information here, but we're just returning a function ref. Okay, so if it's a tail call thing, I think that we could make a program that exercises these spots. Yep. All right. It is 3:34 by my watch. So I think that what I would like to do is, rather than try to fix the tests, we're going to go into our compile thing, and select instructions is a pass. So we are going to go down here. Okay, so it comes after explicate control. So we're going to uncomment all of this business. Okay, and then we're going to use, because we've got new phases in this chapter, we're going to replace those. Oops. Okay. And then x86 needs to be an alias. So import EOC langs x86 def call queue as x86. And then we just do that. Okay. And then we need to import that. Okay. So I think that this will either break, which is very possible, or it will it'll give us something interesting that we can play with. So let's run luster dev. And if you haven't seen this yet, this is your lucky day. Okay. All right, so let's get, I want to get something that is kind of interesting, and we maybe have some example in the book that we can just copy paste and see what it produces. And I think that that's true. And I did not mean to go back to the beginning. They do have one. Right, so we could use tail sum. That's an interesting one. And let's go to, let's first make sure explicate control is correct. Okay, so this is the C-like language that gets generated. So main here assigns tail sum the function ref to temp1. It calls temp1 with the arguments 3 and 0 and returns temp2 plus 36. Again, this is not really C. It's C-like. Okay, and then the tail sum function says if EQ N1 goes to block 1, right, etc. So here's our tail call, right? Let's go to select instructions and see what gets generated. Okay, so we have global align 8 main, and we're annotating the we're annotating the entry points, right? Okay, so main is, so we put the address of tail sum into temp1. I need to put spaces in there in our formatter. Okay, and then so now what were the B? I don't have that. Come on. I don't have that key combo on this machine. Okay, so if we go back here to the argument registers, note it's loading 3. So this is the body of the program, right? It's loading 3 into RDI, right? It's loading 0 into RSI. And then it's doing that indirect call of temp1, which we loaded the address of tail sum. And then it moves REX into temp2, and this will get eliminated, right, later. And then it moves temp2 into REX, and then it adds 36, so that's this, and then jumps to main conclusion. And there's no main conclusion yet. All right, let's look at tail sum. And I'm going to indent a little bit for formatting's sake. Okay, so tail sum, so it takes 2 arguments, N and R. All right, so it moves RDI, which is the first argument, into N1, which was a renamed variable. Cool. RSI, second argument, into R2. That's looking good. And it checks if N1 is equal to 0. That's this. If it jumps if equal to tail sum block 1, which will be this branch. And then otherwise it unconditionally jumps to tail sum block 2. So block 1 says move R.2 into REX and jump to the conclusion. So ultimately conclusion would do a retq, right? To return to this and pop the stack and all that. Okay, and then tail sum block 2 says, get the address of the current function, basically, and put it in this temporary variable. Move N1 into temp2. So moving it into a temporary variable. It may not be necessary. We'll see. Subtract 1 from it. Move N1 into temp3. Okay, so this comes from the remove complex operands bits. Add R.2 to temp3. So now we have temp2 and temp3 will be the arguments. So move those into the argument registers and tail jump to temp1, which was the address of that. So that looks pretty good. Need to fix a few formatting things and then we'll call it. And we can do some more interesting tests next time. So if we go here, and I think that the issue is we need a comma space on that LEAQ. Right. Now those look correct, right? Um, there's some business going on here that we need to fix with the formatting of. So this is put a tab before. What's going on? Okay, so it's interesting that's indented. Format instructions adds. Does that add indentation to everything? Um, it has to do with this. This gets, because this prefix is here, this gets indented on that line. And I wonder if we do this, if that fixes it. No, that just gets it. And I think what was happening was before. Let's look at x86 global. Format block. Yeah. I mean, we straight up copied that. The difference is that's the only difference. It's longer. I'm so confused. I don't know why it does that. That's really weird. Like, these don't get indented, but these do. Huh. Okay. I mean, it's not technically correct, but I don't know. There's some subtleties to the layout algorithm that I'm not getting, so we'll have to figure that out later. The other option is that this group. Rather than putting this prefix in there, we prepend the prefix on this entire document. Let's try that real quick and see if that happens, if that works. Oops. Yeah, that comes out correct. Okay. We'll keep it like that. So, yeah, this is just weird, like, nesting of documents thing for that pretty printer. Okay, cool. Thank you for hanging out. We'll see you, I hope, next week.